Hi everyone, my name is Bhaskar Roberts, and I'll be presenting our work, Quantum One-Time Programs Revisited. This is joint work with Aparna Gupta, Jiahui Liu, Justin Raizes, and Vinod Vaikuntanathan. So what is a one-time program? This is a piece of software that you can evaluate once on any input of your choice, but after that, it becomes useless and stops responding to additional queries. It is known that one-time programs are classically impossible. You can't construct them with classical computers without making additional hardware assumptions. And the reason for this is simple. You can simply take your classical software representing the program and make many copies of it. Then you can evaluate each copy on just one input, and in this way, evaluate the software on many inputs. However, in the quantum setting, the picture changes. We have the quantum no-cloning theorem, which says that quantum states are in general unclonable. And so the copying attack from before doesn't necessarily work. This presents the following question. Can we construct quantum one-time programs? The idea would be to take our program and represent it as a quantum state so that anytime the user measures the output of the program, it's a destructive measurement that destroys the state and makes it useless for answering future queries. It turns out that maybe we could construct one-time programs in the quantum setting. In 2016, Ben David and Satuth constructed signature tokens, which are essentially quantum one-time programs for the signing function. So they show that given their quantum signing key, you can sign any one message of your choice, but you can't produce signatures on two different messages. So in light of the signature tokens result, we could hope to construct quantum one-time programs for a larger class of functions. However, there are a few roadblocks that we have to be aware of. Broadbent, Gutowski, and Stabila defined a very strong notion of security for one-time programs and showed that essentially only trivial one-time programs exist. No non-trivial one-time programs satisfying their security notion are possible even quantumly. Additionally, we shouldn't be able to construct one-time programs for deterministic programs. These are programs where the output of the function is completely determined by the input. And the reason for this is that when you measure the output of this function, it's always a gentle measurement. It doesn't perturb the state. So if you have a quantum program for this function, you can measure the output and then rewind back to the original state. So this is the state of affairs regarding one-time programs, and our work makes progress in a few directions. First, we provide a construction of quantum one-time programs for general functions, and we show that it's secure for quote-unquote unlearnable programs. This construction is in the classical Oracle model. Next, we also provide a strong simulation-based notion of security called SEQ security and show that our construction satisfies it. This is significant because it is achievable, and we find that it implies a lot of other operational security definitions. We also present a plane model construction by instantiating our Oracle model construction with post-quantum secure I/O. And in this way, we construct one-time programs for constrained PRFs. Finally, we present some applications of our work. We will start by talking about our construction of one-time programs, and then later on, we'll show how to analyze its security. The first tool that we will use are subspace states, which were defined by Aronson and Cristiano in 2012. A subspace state is a superposition over vectors in a subspace. In particular, we sample a random subspace of dimension lambda over 2 and create a superposition over all the vectors in the subspace. This state has several nice properties that are cryptographically useful. First, you can measure this state in the computational basis to get a vector in the subspace S. And you could also measure the state in the Hadamard basis to get a vector in the orthogonal subspace S perp. This state has essentially an uncertainty relation, which says that you can't learn both. You can learn either a vector in the primal subspace or a vector in the dual subspace, but not both. And it turns out that this direct product hardness holds even if you give out membership oracles, which are indicated as OS and OS perp. These are oracles that decide whether a given vector belongs to S or S perp. Subspace states are useful for our purpose because they directly give a construction of signature tokens. So let's take the subspace state and make that our signing key, and the oracles will be the verification key. If you want to sign the message 0, you measure the state in the computational basis, and the vector that you obtain is the signature. If you want to sign a message 1, you measure in the Hadamard basis and get a vector in the dual subspace. Now, the security guarantee of these signature tokens says that you shouldn't be able to obtain a signature on both 0 and 1. And this is exactly what direct product hardness gives us. Furthermore, the direct product hardness does hold even when the oracles deciding membership in S and S perp are public. So the verification procedure using these oracles is public. Now we'll see how to use the signature tokens to construct a one-time program for any randomized function. To start, we will just look at functions that have a single bit input. You can see the syntax here. The function f takes a user-defined bit as input, then it samples a random string r and uses both of these values to compute the output y. The main idea for our construction is this. The user is asked to sign their input bit using a signature token. We will give the user the subspace state that we saw earlier, which will act as the signing key, as well as this oracle that computes f, and together they represent the one-time program. Notably, this oracle only computes an answer if the input bit x is accompanied by a valid signature. For example, if the user wants to query the function on x equals 0, they have to provide a vector v that belongs to the primal subspace. If so, the program will compute f of 0 on a random string. Now, this construction isn't yet secure for the following reason. The output of the oracle is not entangled with which vector v was used to sign the message. We want it to be the case that measuring the output of the oracle will collapse the signature token, rendering it useless for future queries. But with this construction as written, the output is f of 0, r, which doesn't depend on which vector v was used to sign the message. So after measuring the output of the oracle, the user could rewind the program to the original state and recover the signature token. And then they can use the signature token to sign additional messages. So the second idea that we need to make this construction secure is some way to entangle the output of the oracle with the signature token, so that measuring the output destroys the token. And this is how we do it. Now note that the random string r is computed as the hash of the vector. The hash function in this case is a random oracle. So now the output of the oracle will be highly entangled with r, assuming that the function is randomized. And the value of r will be entangled with the value of v. So if we measure the output of the oracle, the signature token collapses. Now we will generalize our one-time program construction to work for functions with n-bit inputs. So rather than allowing the user to specify a single bit, they can specify a bit string of length n. The main idea for this construction is to ask the user to sign each input bit using a signature token. So we give the user n independent signature tokens, along with essentially the same oracle as before, and together they represent the one-time program. Note that this oracle only computes an answer if every bit of x is accompanied by a valid signature, and it computes the random string r by hashing all of the signatures together. As I mentioned earlier, we believe that this construction is secure. It satisfies a reasonable notion of one-time security if the function f is sufficiently random. However, it's not yet clear what the right notion of security is, and we'll get to that in the second part of the talk. I'll also mention that there is a concurrent work by Gunn and Movasig, which presents a similar construction, but with a different notion of one-time security that is simpler but weaker. Now I'll talk about the challenges involved in defining the right notion of security. Let's start with the simplest reasonable way to define security for a one-time program. It basically says that the adversary can't evaluate the program on two different inputs. In cryptography, we like to define security in terms of games between a dishonest adversary and an honest challenger. So in our one-time security game, the challenger will send the one-time program to the adversary, and the adversary will send back two evaluations of the program. This might be a message followed by a signature, or something else that's verifiable. And the challenger will verify both of these evaluations, and we say the adversary wins the game if both verifications are accepted. Finally, we say that this construction of a one-time program is secure if every adversary has only negligible probability of winning this game. So in short, we say that construction is secure if it's hard for an adversary to find two evaluations of the program. This is a reasonable notion of security, but depending on the setting, it may not be enough. For example, it might be possible for the adversary to learn all of one output and half of another output. This is not ruled out by the operational security definition, but in many applications, this would represent a significant breach of security. Additionally, we might want our program to satisfy some indistinguishability property, like for a pseudo-random function. And again, the operational security definition doesn't provide meaningful security in this setting because operational security only says the adversary can't learn two complete outputs. Typically, when we are confronted with issues like this, cryptographers reach for simulation-based security notions, which tend to be stronger and imply a lot of these other operational security notions that we want. As our next attempt at defining security, I'll present a typical simulation-based security notion. At a high level, the simulation guarantee says that anything that the adversary can learn from the one-time program can be simulated in an ideal world where access to the function is perfectly restricted to making only one query. So to be more precise, there is an ideal world and a real world. In the real world, we have the actual adversary with the actual one-time program, and they will try to compute some output function. In the ideal world, we have a simulator that tries to match whatever the real world adversary is computing, but the simulator has significantly restricted access to the function f. Specifically, they'll have some sort of idealized oracle that only allows one query. And in the end, the real-world adversary and the simulator have to send their outputs to a distinguisher who should not be able to guess whether what they're seeing came from the real world or the ideal world. And if the two worlds are indistinguishable, we say that this construction is secure. So to get really technical, this is what the definition would look like. It says, for all real-world adversaries, there exists an ideal world simulator such that for any function f and any distinguisher, the adversary's output in the real world is indistinguishable from the simulator's output. So that is a typical simulation-based security definition for one-time programs. The place where this gets tricky is how we define the one-time oracle. In other words, how exactly do we limit the simulator to making just one query? To illustrate why this is a tricky question, let's try defining our one-time oracle in the most obvious way. So in this definition, the oracle answers one quantum query and then it self-destructs. It just stops responding to queries. Is this a good simulation-based security notion? No, it is not, because it's not achievable. And we'll see an attack that allows you to distinguish between the real and the ideal world. Basically, the real-world adversary will send their one-time program to the distinguisher, and the distinguisher will query the program on two random inputs. Of course, they will have to uncompute their queries in between so that they can actually do two queries. The simulator has to output something that can match that behavior. To make things simple for this argument, let's say that the simulator outputs the oracle that they were given access to. However, this oracle is not as good as the actual one-time program, as we will see in a minute. So we're going to do what's called an uncomputation attack. We're going to make a query, make a gentle measurement that doesn't perturb the state, and then uncompute the query, and we get that query essentially for free. So the distinguisher will query the one-time program on an input x1, and let's say that this is something verifiable like a signature scheme. Then they can verify the output of the one-time program, verify that it was correctly computed. And the only measurement they make is the output of verification. So they're going to get the answer 1 with overwhelming probability, which just tells them that the program computed the answer correctly. And because this answer is 1 with overwhelming probability, this measurement is gentle. It doesn't perturb the state. And so we can uncompute this query and recover the original one-time program. Now the distinguisher can repeat the same procedure with a new input x2, and they will get the same outcome. So on both of these queries, verifications outputs 1. Now let's look at what happens in the ideal world. The distinguisher makes their first query as normal, and then the oracle self-destructs. That will be a problem later on. Then the distinguisher runs verify. They measure the output and they get 1 because the program computed correctly. And now they can try to uncompute the query, but they don't end up with the original program state. They end up with the self-destructed oracle. Now, if they try to repeat this same procedure on a second input, they're not going to get the same answer. Verification will reject because they're not computing the answer using the correct oracle. They're computing their answer with the post-destruction oracle. And in this way, the distinguisher can successfully distinguish the real world from the ideal world. Another way to phrase this is that there are things the adversary can do in the real world which cannot be done given just a single query to this oracle. So this seems to doom our attempt to construct a simulation-based security notion. But let's look at the problem in a different way. There are, let's call them gentle queries, in which the adversary makes a query to their program. They make a gentle measurement, and then they uncompute the query to obtain the original program state. This is not something that we can prevent in the real world. These gentle queries are always going to be possible for any one-time program that we give out. However, we don't actually need to prevent gentle queries, because if the function f is sufficiently random, gentle queries don't tell the adversary anything useful. It's only the destructive queries that actually tell the adversary anything meaningful about the output of the function. So that's the key idea for our new security definition. We will allow the ideal world simulator to uncompute gentle queries for free. So we propose a new ideal world oracle, and we call this model the single effective query model. In this model, the simulator can make any number of gentle queries as long as they uncompute them, but they can only make up to one destructive query. This would be like, for example, computing the signature on a message and then measuring the signature. So we can actually record the number of destructive queries that have been made using the compressed oracle technique. At a high level, this technique allows us to measure the entanglement between the adversary's registers and the program's internal randomness registers. And if the function is sufficiently random, any query that tells the adversary useful information is going to create entanglement between these registers. So we define our oracle to measure whether there is entanglement or not. And if there is entanglement, it basically shuts off and doesn't answer additional queries. Finally, our notion of security is called SEQ security, and it looks like the standard simulation-based notion of security that we defined earlier. The key distinction is that the ideal world simulator gets access to the SEQ oracle. Okay, so we have our new notion of security. Is it any good? We think so for the following reasons. First, SEQ security is achievable. We show that actually SEQ security is achievable for any randomized program using the construction that we saw earlier. Even if the program is deterministic in the sense that it ignores its randomness. This might raise a red flag, like we shouldn't be able to construct a one-time program for deterministic programs. But the way around this is to note that SEQ security is not meaningful for deterministic programs, in the same way that obfuscation and copy protection are meaningless for learnable programs. The second reason why we like this definition is that it is meaningful for sufficiently random programs. Specifically, we call them SEQ unlearnable programs. And we show that SEQ security implies the operational security notion that we saw earlier for SEQ unlearnable programs. So for this class of programs, we show that the adversary cannot learn two input-output pairs of the function. Some examples of SEQ unlearnable programs for which we can achieve operational security are truly random functions, functions that are both pairwise independent and highly random, and also certain functions constructed from blind unforgeable signatures. Some examples of SEQ learnable programs for which we can't hope to achieve operational security are deterministic programs, like I mentioned before, and surprisingly, even some highly random programs as well. I would call them partially deterministic. We'll see an example of one on the next slide. But this state of affairs should match our intuition. For most highly random functions, typically with a pairwise independence guarantee, we can achieve operationally secure one-time programs, and for deterministic programs, we cannot. Next, I'll present that example of a high min-entropy function, which is nevertheless SEQ learnable. So it looks like this. R is the random string that is factored into the output. And it turns out that if you're given SEQ access to this program, or really any quantum one-time program for this function, you can completely learn a description of the function. And the attack works by making gentle queries and uncomputing them. So here's how it works. The adversary first queries the program on input 0. And now note that the output of the function has the property that the first chunk is a deterministic string A, the second chunk is highly random. So the adversary will only measure the first chunk. They'll learn A, and this is a gentle measurement. Now they can uncompute that query, and essentially they have learned A for free. Next, the adversary queries the function on input A. Again, it's the same state of affairs. We have the first chunk being a deterministic string K and the second chunk being random. The adversary will just measure K. Again, it's a gentle measurement and they uncompute it. At this point, the adversary has a complete classical description of the function, and so they can compute it on any input. Whereas in the ideal world, if you only had one quantum query to this function, you could not learn K. So here are a few lessons that we can take away from this example. The main one being that it's not the case that every high min entropy function has an operationally secure one-time program, because if the function is partially deterministic, the adversary can learn a description of the function by making only gentle measurements. Next, I will just briefly touch on our plane model construction. The construction that we saw earlier assumes a classical oracle. We will instantiate the classical oracle using I/O. And we show that assuming post-quantum secure I/O and LWE, we can construct a one-time program for randomized constrained PRFs. We also give an impossibility result that says that there exists an SEQ unlearnable program that has no secure one-time program in the plane model. So it suggests that the plane model and the classical oracle model are meaningfully different. We also present some applications of our one-time program construction. First, we construct more signature tokens. We show that any blind unforgeable signature scheme can be compiled into a signature token. And this should make intuitive sense. After all, signature tokens were the first example of a secure quantum one-time program. So it should be expected that we could construct signature tokens from one-time programs. We also construct one-time Nizhik proofs that allow the prover to prove just one statement. And we construct quantum money from any verifiable one-time program. Finally, we have some open questions. First, what is the strongest achievable notion of one-time security? We believe that SEQ security is a good candidate, but it's not clear. Second, what other applications exist for one-time programs? We've already covered several applications in our work, such as signature tokens and one-time proofs. Gunn and Movasig also suggest that generative AI might also provide some applications. Third, can we construct more general one-time programs for quantum channels? Our construction currently just works for classical randomized functionalities. It's not clear how to generalize beyond that. And that's everything. Thanks so much for listening, and please feel free to reach out with any questions you may have.